Imagine a student preparing for a final exam. Instead of learning the underlying concepts, they memorize the exact answers to every single practice question. They ace the practice test, scoring a perfect 100%. But when the final exam arrives, with new questions they've never seen before, they fail spectacularly. This student didn't truly learn, they just memorized. In the world of artificial intelligence, we call this problem overfitting. Let's visualize this with a machine learning model, a digital brain designed to learn from information. A good model, our well-generalized model, looks at a set of data points and learns the fundamental pattern, the true trend hidden within. Now meet its counterpart, the overfitted model. When shown the same data, it doesn't just learn the pattern. It obsessively memorizes every single point, including random noise and insignificant details. It wraps itself so tightly around the training data that it perfectly accounts for every dot, every outlier, creating a complex and contorted map. It has aced the practice test, but it hasn't actually learned the subject. The real trouble begins when the test comes. On a graph, we can watch this happen in real time. As the model trains, its error on the training data or training loss drops steadily towards zero. It's getting better and better at memorizing. But if we track its performance on a separate set of test data it has never seen, the validation loss, we see a different story. After a certain point, while training loss continues to fall, the validation loss begins to rise. This is the moment overfitting takes hold. The model is now so specialized in the training data that it's becoming worse at handling anything new. When we present our overfitted model with new, unseen data points, its predictions are wild and inaccurate. It's trying to apply its hyper-specific memorized rules to a world that doesn't follow them, leading to catastrophic failure. So what causes a model to become so obsessed with details? One major cause is excessive complexity. Imagine the overfitted model as a ridiculously intricate and tangled neural network with far more connections than necessary. This complexity gives it the power to memorize noise instead of being forced to find a simpler, more general pattern. Another culprit is insufficient data. If we only show the model a handful of data points, it's easy for it to just memorize their exact positions. There isn't enough information to reveal a broader trend, so memorization becomes the path of least resistance. Finally, noisy data can trick the model. If the training set is filled with irrelevant or random information, the overfitted model will dutifully try to find a pattern in the chaos, incorporating that meaningless noise into its logic. Thankfully, we have a toolkit of strategies to combat overfitting and guide our models toward true learning. One technique is called early stopping. By monitoring the validation loss, we can simply halt the training process right at that sweet spot, just before the model starts to overfit. Another powerful method is data augmentation. We can artificially expand our dataset by creating slightly modified copies of our existing data. For example, we can take an image and create new versions by rotating it, flipping it, or changing its brightness. This teaches the model to focus on core features, not superficial details. We can also use regularization, which acts like a force that penalizes complexity. It gently pulls on the overfitted model, simplifying its tangled web and encouraging it to become a cleaner, more well-generalized shape. Lastly, cross-validation involves splitting the dataset into several smaller sections or folds. The model is then trained and tested multiple times, using a different fold for testing each time, ensuring it performs well across all the data, not just one specific part. In the end, building a great machine learning model isn't about achieving a perfect score on the data it already knows. The ultimate goal is to create a model that generalizes, one that can take its knowledge and apply it successfully to new, unseen situations it will encounter in the real world. We want to build the well-generalized model that gracefully and accurately navigates a constant stream of fresh data points, providing real value while the confused, overfitted model is left behind, lost in the details of the past.